So this is joint work with my former student, Carol, now at University of Wisconsin at Madison, basically his thesis work. And thanks for inviting me to this memorable conference. So I met Partha, I think probably 6 years ago when I gave a talk at the Statistical Department in Chicago here. And Partha and actually Misha came up to talk to me. I had known his work before I came to give a talk. And the most recent memorable conversation I had was about 2 or 3 years ago. We were both at the Oberwolfach Mass conference, statistical conference in the Mass Institute in Oberwolfach. And actually, I think Vladimir was also there. And we took this long walk. If you have been to Oberwolfach, you know there's always this long walk to get some Black Forest cake. So we were together on this long walk. Took, I don't know, like an hour or two. And we got into this discussion about what's the best to kind of make statistics more known to other people. We both felt like statistics so useful, but somehow it's this hidden treasure. And Partha was saying that you guys should do better advertising your field. Well, he's part of statistics, and then he said you should just call statistics as the theory or something of concentration. So I thought that was a good idea, and I hope that you'll see that concentration is very much the key to a lot of the analysis, and I'll be able to show you that's the one most interesting, I think, result from our paper is actually about concentration. So here's a run of my talk, and I think I should go pretty fast. I have 13 minutes. And we just giving you a brief overview of spectral clustering, and I'll tell you our work, which is attempt try to analyze this well-known algorithm in a different type of spectral framework than what existed before us, and then some generalization to the directed case, and I'll end with some preliminary analysis of the Enron data. So networks have been all over news or scientific papers, and some probably more meaningful than others. And I want to point you to this critique of this famous work by Chris Takis and Fowler about if you associate with obese people, make you more likely to be obese. Right? It was all over the news. But I think the causal inference is very much in doubt. I recommend you read Russ Lyon's critique from University of Indiana in Bloomington. And here's some basic notation. So we have a graph with V as the vertex set and E as the edge set. And if you want to find the clustering community that detection or partition, you could try to find something called a graph cut, have an objective function. You try to maximize or minimize. Often you end up with an NP-hard combinatorial problem. And spectral clustering can be viewed as a convex relaxation of the graph cut problem and can be traced back to this electric network partition in Fiedler in the 70s. And there's this book by Chong. And recently, the incarnation of this field has been a lot because the two papers, Shi and Malik, for image segmentation. And there was a follow-up paper on NG who generalized it. And there's connections and two good reviews. And when you have adjacency matrix matching relationship between two nodes to make life simple, I'm going to just stick with for the theoretical analysis when you have the weights 0 or 1, but you could do continuous weights. And you have the degree matrix, which is DII. And there are many different forms of Laplacians, which the spectral clustering is based on. So the Laplacians, you could be just removing the degrees from the adjacency matrix. You have a normalized version through random walk, which is behind the page rank of the early version of search engine by Google. And you have this normalized version. So in my analysis, I would just remove the identity since the eigensystem is identical to make life easy for myself. And why the Laplacian have anything to do with partition? So there are these earlier works showing that through Cheeger's inequality, actually the partition, the eigenvalue of the normalized Laplacian is closely related to the conductance of a graph. So this is evidence why the eigen decomposition has anything to do with partition. And also, if you take the random walk version of the Laplacian, then the mixing rate of this random walk have some, it's determined by the eigenvalue. So that just says that if things are more relatively flow, like connectivity is good, then things can mix better, and therefore you don't have much clustering structure. And the more recent analysis of spectrum very much had to do with the Partha Niyogi paper. That's the first time I saw the analysis, actually before I read about the triggers inequality stuff. So those are under continuous assumption. Basically, your data come from some continuous attributes. And then from those attributes, you form the W identity matrix, maybe through a kernel. Then you can ask the question, if you do come up with the weights that way, if the data come from a manifold, can you use the spectral clustering to try to recover that? And there was related works on that. And more recently with Tao and Michel, we did some basically analyze the same kind of related algorithm under a different set of assumptions, more towards clustering. But we assume still continuous data, you have a mixture of Gaussian. So here just maybe a pictorial illustration of the algorithm. So you have now actually generated the data through a discrete model. So not continuous manifold model, but a discrete model from social networks called the stochastic block model. So you have community of people, and there are 3 clusters that you can guess from their mole on the diagonal, and you try to discover the communities. So it's the same algorithm, but for different type of data, and you could do eigenvalue decomposition of the Laplacian, the symmetric Laplacian, and then you take 2 eigenvectors, and you clearly see the 3 clusters. After the projection, almost like PCA, you don't have to do k-means, but in my analysis, I'll analyze the k-means version. You could do hierarchical, many other clustering algorithms can follow. Okay, so what I'm trying to do here is try to kind of use an algorithm, something I want to understand, and analyze it under a stochastic model, which didn't give a rise to the algorithm. So it's like, this is spectral clustering, doesn't have a statistical underpinning, and I'm going to say that, suppose I have a good statistical model, and the communities are well defined. Can I show that the spectral clustering actually finds it? So itself doesn't really say that it's a good algorithm. But if the algorithm has been shown empirically very successful finding meaningful, validable criteria, clusters, and this type of analysis just adds evidence to why this could be algorithm. So it's not like I'm believing that the stochastic block model is actually true in real life communities, but just simple enough model that if the spectral clustering doesn't work, that will raise a flag for me. That will say, well, then if cannot even do well with such a simple model with well-defined communities, then it will put doubt on why it should work in more complex case. So it's under this kind of thinking, I'm doing this analysis. And stochastic block model, it has existed in the statistical literature since the 80s, and there's some recent analysis and review. So if you really believe stochastic block model, you might say you should do maximum likelihood. But in the modern data era, a lot of times we have data, we don't actually have a good generative model. That's why the algorithm approach, I think, is very important. But this type of model can be used for analysis and shouldn't be unique. You might subject spectral clustering model algorithm to other well-defined statistical models. So there's a little difference between the CS approach and statistical approach. In the CS approach, usually, the first one, I think both statisticians and CS people agree that if something works, you have a downstream analysis, you made money or something, and then it's algorithm. Could be a wrong model, but it's a good algorithm. And the CS approach would say that, well, so spectral clustering is good because approximately will solve my NP hard problem. Right, it's a kind of deterministic framework and saying that will solve the problem I want to solve, even I couldn't do it with the combinatorial. And I'm doing it with a different twist, saying that if I subject this algorithm under a stochastic block model, which is stochastic with well-defined community, and it works, that for me is a good property for stochastic block, for spectral clustering. So the stochastic block model, as you can guess, is that you have, say, 3 or 5 communities, and the probability of making a link between the communities is smaller or different from within the community. So each link between any 2 nodes is a random toss of Bernoulli random variable, and the probability don't have to be the same. For simplicity in the statement of theorem, I'm going to say that there are two probabilities within community and between community, but you can do more than any, doesn't have to be the same. And so stochastic block model has been used recently in the literature to analyze other algorithms, not the spectral clustering in the Bigel and Chen paper, but the previous work had fixed the number of blocks, just saying that when n goes to infinity, when you have more and more nodes, but you only have, say, 5 communities. And therefore, that means that each community size has to grow. And there's a good case to be made that we should look at the high dimensional case where you allow the number of clusters grow together with the number of nodes. First, there's this empirical work by Les Kovac et al. 2008, and shown that actually when you have more and more nodes, the size of the community don't go to infinity. And in biology, there's this famous number called Dunbar's number, which these biologists have observed like primates in the wild setting that the community tend to be like 150 and 200. So it's not like when I have more and more animals, the sizes of the community grow bigger. So to accommodate or to reflect these two empirical evidence, we like to allow the number of blocks go to infinity. That's what we call by high dimensional analysis. So as I said, and then we have to say how we're going to show our result, spectral clustering is good or not. We're actually trying to show that every node can be classified correctly. It turns out I couldn't do that, and you might argue that might not be possible because you had the number of information accumulated might not be enough. We're able to show that the proportion of misclustered nodes going to 0. And then to prove this result, we had to prove some convergent eigenvectors of the Laplacian, and it's an interesting result on its own, and that's where concentration is used. So this is a simple case of you have two probabilities, P for block nodes to connect within the same block, and R when they're not. And we want to estimate the membership of each node. So if you recall that I used L to denote the Laplacian, and here, since now I have a stochastic block model, I can use my script L to indicate the population version. Right? In statistics, a lot of times, under statistical model, you have a population version, you have a sample version. And under the stochastic block model, when the clusters are well defined, you can show that this clustering is captured in the population version. Because it's not capturing the population version under the script L, then it's hard for the sample version to discover it. So that's good. And there's some rotation you have to do because the community labeling is not defined. So you have to do some permutation. And so our result basically can bound, let me say, state the result in the simple case. I have two probabilities. P is the within probability, within block probability, and R is cross. I do need conditions on the eigenvalues of the population version, because if the eigenvalues are not well separated, my clustering structure, even in the population case, are not well defined. So I need that. And also the second condition I would like to remove, but right now we have it, is that the expected degree of nodes is the size of the whole population of nodes. And that's like a dense graph. And we know that in practice, graphs tend to be sparse, not dense. But it could be artifact of analysis, or you need to look at other methods. So that's the degree is kind of dense. And for a small network, the referee actually asked us about the question. The paper appeared in Annual Statistics. The referee didn't like it, and to be honest, we didn't either, but we couldn't remove it. So our response to the referee was that for a small network, say a college of 1,000 students or 2,000 students, and if you have 200 friends or connecting on Facebook, so this dense is only order n. It's not too unrealistic. And for large networks, actually, you usually don't apply, because computation constraint, the spectral clustering on the whole graph. You actually apply to subgraph. So whatever you're applying to on that scale is not horrible. And we can bound the number of misclassified or cluster nodes by k to the power of 3 and log n. Log n doesn't really bother me too much, and it's kind of power of k. Is that optimal? I would guess it's probably not, but it's a pretty strong result. And this will accommodate the number of clusters go to infinity at a speed a little slower than n cubed. Okay, cube root. And the key proof in the result is this concentration, right? That's where exactly was Partha's point when we had that long walk. Is that in statistics, large numbers, that's consistency, asymptotic normality, that's central limit theorem, and now in the new era, we talk about concentration, but it's about things stabilize. And if you look at L, which is the Laplacian, observed Laplacian matrix, the D under my stochastic model actually almost like constant, so it doesn't really give us any problem. So the W, but W is a random toss. Doesn't matter how big your W grows, it never concentrates. Just random toss. You basically have a matrix with random tosses for each entry. It's not going to stabilize. However, if you do L times L symmetric or L to L transpose, it's the same thing. This matrix entries concentrate. What happens is that you're counting for any two nodes, the number of shared neighbors. And that's a summation, and that concentrates. And the good thing about the relationship between the eigensystem L and LL is that the eigenvalues are related by the square, and the eigenvectors are identical. Okay? So even though L doesn't concentrate, but LL does, and the eigenvectors of LL are the same as the eigenvectors of L. And therefore, you have the Frobenius convergence for LL, so therefore by this Davis-Kahan theorem, you know that the eigenvectors also converge, and because the L and LL share the same eigenvectors, and therefore the eigenvectors of L, which is what I care about, also converge. So that's where we did have to have this concentration to move from sample version to population version. But if you look at the Laplacian, it doesn't. So this, you can say that actually, this is a modified relation between any two nodes. So with the original node, like graph, I'm basically constructing a new similarity between nodes, which is the shared neighbors. And you can see that's more stable. That's the theorem says under stochastic block model. Even in real life, you may say that, well, it's better to say whether the two people have a real relationship because they have shared many friends than just like there's a link, right? So, and then we later discovered that people already actually use this as a similarity metric. We came out with this because analysis, but people already have used it to just as a kind of a modified measure. And what time do I have, Misha? What? 15. Oh, 15, so I can go slow then. So now move to the directed graphs. And so there are many network data are not symmetric, right? There's this famous Enron investigation. How many of you are old enough to know it? So the emails all on online, so you can take a look. So for people who haven't heard about it, so Enron was an energy company based in Texas, and in the late 90s and early 2000s, they were, one version was that they were manipulating the price of energy, and then they were supplying to California, and then California had rolling blackouts and then lost a lot of money. So then there was a criminal investigation into Enron company, and all the emails were public. So you have 154 employees, and the emails between them are open, and so we're only using the counts between the two nodes and using the context of the emails as kind of validation to see what we found. Okay, so I'm using AIG as the number of emails from I to J. So this is very directional, right? I think in your own email network, probably there are certain people you probably send emails more than they send to you, and vice versa. I would say that there's never a really symmetric relationship. So relationships often have a direction, and if you take the vanilla Laplacian, then that's an asymmetric matrix. And if you do the eigenvalue decomposition, you end up with compact values. And many of the existing works just summarize the relationship and go back to the vanilla spectral clustering. Basically, you're kind of looking at the averaged relationship between one direction and the other. And we just said that, well, we should just do singular value decomposition until like last week. We didn't find any references, but last week I gave a talk at Purdue and I got a few references, which was no surprising that people have used it about 10 years ago. So this is a simplified version that you have a relationship of I and J and directional. So Wij is whether you send email from I to J and the other way around. So they might not be equal because you might not be, some people might be only receiving, some people might be only sending. And the degree now has two degrees, right? The sending degree or the parent degree, that's the receiving degree, and the offspring degree with the sending degree. So if you want to make it symmetric, you use both degrees to weight your original adjacency, now asymmetric adjacency matrix. You basically just counting number of parents and number of offsprings and weigh the relationship by some average version, geometric average version of that. And the idea is very simple, right? Now I have an asymmetric matrix. I can do singular value decomposition. I have a left eigenvalue decomposition and right eigenvalue decomposition. And in theory, you don't even have to take the same number of components. Basically, you're looking at the same number of nodes in two networks, right? One is the receiving network, one is the sending network. And you can have different number of clusters. But now I'm just making the canonical version that actually I take the same number of leading eigenvectors and then compare them. So I want to use this decomposition to understand the asymmetry of the relationship. And as I said, basically you have two sets of clusters, and you can actually see that the SVD has an interpretation if you look at the square matrix or if you look at the shared number of neighbors. So this is algebraic result saying that single value vectors can be viewed as eigenvectors of a symmetric matrices. One is L transpose, the other is L transpose L. And basically these are the relationships, as I said, looking at shared parents or shared offspring. And we kind of came with this also again because of the theory, because of the concentration result, and we liked the L. And later last week I discovered that actually the SVD has been used in the Kahneman His paper, and then Indigit Dillon had the 201. He was looking at actually document versus author or something. So the two directions are not the same. But in the space it's just SVD, and they usually have looked at only one direction for partition. So we're kind of doing more because we're parallelizing with the spectral clustering, and we're doing clustering. And so these are the definitely related works earlier. So now let's take a look at Enron data, right? So if you look at the Enron data, and I actually used the count, email counts. I didn't use just yes or no. And those are the eigenvalue plots. And the first eigenvalue actually corresponds to the degrees. And you could use it, and actually under the stochastic block model, people can show that if you just use the degree, you get pretty good clustering. But since I'm not really wholeheartedly believing the stochastic block model, we didn't use that. We actually didn't use that, the first one. You could have used it. We used the 3, 2nd, 3rd, 4, and 5. So we use because there's a jump. And it's a question, how do you take the jump? If you stochastic block model, probably can do some thresholding. But since, again, I don't think that's the right model for this data, I just look at the visual display and took the first 5, and then didn't use the first one. Okay, and then so we did a single vector decomposition. And we measured somehow the difference. So you have 2 projections now. Each node gets projected to the left space and the right space. And then you want to see that how similar they are. And you look at the distances of the left and right, or see how symmetric the 2 relationships are. You mostly have quite close, but then you have this guy way out. So this is a person. One type of relationship is very different from the other type of relationship. And because the Enron data we have so much information, you have everything, right? You know this person's identity, their name, and everything, and you search on the internet. And actually, this guy has a name and it's a. So I'll just let you read. So last time I gave this talk, and I think it was in Minnesota IMA, and one guy emailed me later and said, "Oh, I like your talk, but I thought you were too political." He thought I was taking sides. So I try not to say anything this time. Let you judge. Yeah, this guy has a different explanation why the California blackout happened. So I thought I should be objective and be a statistician and leave you to decide. Yes.
So the point being an outlier is saying what? That lots of people sent this person message and he sent you, or what?
No, actually, this way, when you look at the data, you can see is that he sends emails to a lot of people, but people don't send to him. So somehow, some people can say this is like a bottleneck in some information flow, right? This is a key guy who seems to be, there's not a lot of back and forth, just like pushing the information out. And I didn't look at all the emails. You can theorize that maybe he's doing a lot of this stuff, right? Just giving, and if that's what they're doing, right, then you don't want a lot of people know, right? The fewer people you know. But this is, I'm just dreaming now. I don't have hard evidence. So, and it's technically, you can do the same thing for devise a asymmetric stochastic block model and show similar results. So that's just, you can see that the mass will just, there's a parallel mass. So do I have time if I have to show you more data? What? I have, okay, so I didn't think, I think Rob probably finished early, that's why I have longer. So then the question is, would I have seen this guy, if I did the symmetric analysis, right? So what I'm showing here is that, remember, I have 2 clusterings, and I cluster them each into 5 clusters. And this is the index of one direction, that's the other. So this guy really on its own in one direction, doesn't cluster with anyone. And if you do the symmetric analysis, this guy still stands out. So you have seen him. However, this is the left analysis, this is the right analysis. And you can see that this is just the average standout, and this you can see that for one direction, for receiving, he's not as outlier as the sending behavior. He's really, really out there. Of course, for this small network, in theory, you can use the symmetric analysis and identify the person and just take a look, and you know the information. But for much larger networks, usually it will be much harder to look at everyone. This is kind of analysis, kind of like flag people, maybe for you to take a look, right? It's just more systematic. For small networks, you can just take one person at a time. Yes?
Do you have explanation for this?
That's a good question. I have been wondering about it. I don't have it. And I was reading somebody else's paper. I see that too. So there could be 2 possibilities. One is that this is a spectral embedding, and you can also do spherical embedding. If you do that, for the other data people have worked on, you don't see it. So that's a good question. I would like to know the answer. I don't have a good explanation. For some other data set, you have explanation.
Your outlier here is basically somebody, the inflow is extreme, so that you could identify directly by looking at the inflow. Are there some properties that emerge from the eigenvectors that are not as straightforward as inflow or outflow?
Yeah.
In these networks?
Well, we let me show you some further. So we look further, right? This guy just stands out, right? And then we look at. So basically, we do this what's called I-plot. You just shade the same people in all 4 plots and see whether you see a difference in relationship. That's how we have been visualizing. So it turns out that these 2 people is not really much away from the population, but have a different relationship for one and the other. And turns out that they're not very interesting. Their 2 secretaries have a little different patterns. So this is more for what we call EDA. It's not formal analysis. You see, like doing this plot, you bring out more information in the asymmetric version than the symmetric version. Whether that difference of the 2 directions bring up something you wouldn't see otherwise. And so we're just basically looking at things, and there's another person. We just basically pick a point and see whether there's a difference on these different 3 plots. So this is another person which seems to be quite different in terms of one type of relationship versus the other type. And they all have names. What?
Why is it that high?
Well, I'll show you why. Because I look at the, we are just asking. We don't know. Right? The 2 women, of course, didn't turn out to have anything suspicious. Right? So this.
Can you tell that there are 2 women instead of 2 men?
Because they have names. Yeah. For most people, you can tell. But it's true for certain culture.
It's not from the graph.
No. We have all the emails. In theory, you can tag things and click, you get the name, right? But we didn't do that. But we have all the emails. These people are exposed. Yeah.
Since then you know.
Yeah, we have a lot of information because the Enron data is public. But for within organization, people do have this information. If you do this analysis within a company, they do have all the information. But not for outsiders. So this guy also has a name, right? And the other women also have their names, but we couldn't find anything very suspicious. So this is a guy called Jeff Desowich, who is a government relationship employee of Enron. And he seemed to be aware of certain things. But he seemed to say that they didn't do anything wrong. It's an Enron public statement that I have read, including, I think, statement made to financial analysts, state that our exposure in California is not material. And then you look at his email. Now, again, I try to be neutral, and you guys can read. Okay, and then if you search him, he's still working, but he didn't list his Enron experience. And he's from Berkeley. So I think I should. So we haven't completed this analysis because things happen. People graduate, people have kids, and many things. So things have been slow. But we're hoping that just use this as added tool to analyze asymmetric network. Thank you.